Okay, our final example for the day to do with vectors. It's an application of vector addition, and this is in the area of physics, in the area called force. If you don't know physics, have not studied physics, don't worry. This is just something that corresponds to what happens in our day-to-day lives. Force is just naturally applying a pressure, energy, movement, push, a force to something. If we imagine that we have a box, and I push on it this way, as hard as I can, well, that force has two things. It has the direction I'm pushing, it's this direction. I'm pushing it to the right. And it also has a size. The size of the force is like how big of a force you're pushing with. Now, if you are simultaneously pushing on the box the other direction, and we are equally strong, well, your force is going to be going the opposite way, but will have the same length. And what are these two forces going to do? If we're pushing on opposite ends of this box, they're going to cancel out. And the way that we obtain that mathematically is we take the two vectors and we add them together. So if this was our vector v and this was our vector w, then the combined force would be v plus w. This is combined force. If we had v and w written in terms of components, then we could add the components to do it. But just visually in the picture, you can see that vector, if we think of vector addition as starting, taking the one vector, and then imagining that this vector is placed so that its starting point is here, following that vector back, we're going to end up with a vector that goes nowhere. And that means that the total force, the combined force on this object is 0. That means that object is not moving at all. The two forces cancel each other out. So in this case, 0 in this case. And in general, when we think about force acting on an object, the way to think about force is in terms of a vector. It has a magnitude, that's how hard a force you're pushing with, and it has a direction, that's which direction you're applying the force. Okay, let's go ahead and look at a proper example. This is example 22.12. It reads, the forces F1 and F2 are applied to an object. Find the resulting total force F, which is equal to F1 plus F2. We're going to add the two forces to get what the resulting force is. Determine the magnitude and the angle of the total force. Approximate these values as necessary. That means that we can use a calculator. And how do we measure force? Well, force is measured in something called newtons. The international system of units for force is the newton. What is a newton? Well, it's kilograms times meters per second squared. And it somehow measures, it's a little bit like the acceleration, but it's how much is accelerating per unit of weight. So this is the setup. And now let's look. There's two examples. A is F1 has a magnitude of 3 newtons and an angle of 45 degrees. Let's go ahead and see. This is part A, F1. And it says it has a magnitude, so F1, the magnitude. They don't give us the A and the B components. They just say that the magnitude is 3, and that the angle that it's at, theta, is 45 degrees. If we wanted to... okay, maybe we'll leave that. We'll do a drawing in just a moment. And then we look at F2. The magnitude of our second force is 5 newtons, so this one is pushing a little bit harder, almost twice as hard, not quite, but it's not pushing at the same angle. It's pushing at this angle 135 degrees. Okay, what I want to do is a couple of things. The way that we're going to solve this is by first finding the components, like the x and the y of each of these, using the formulas that were brought up at the beginning of this of this lesson. However, what I want to do is just point out to you, to do a sort of a side sketch of where we can expect the resulting force F to end up. So where is F going to be? F is F1 plus F2. And if we draw this guy, here we go. Now these are going to be rough estimates, but the F1 goes at a 45-degree angle, a distance of about 3. So that's like our F1. And then let's see. The F2 is at a distance of, it's at an angle of 135 degrees. That's in the second quadrant. It goes this way. And it goes a distance of 5. Something like this. And I can guess already, if we were to travel first along one vector and then along the other vector, the resulting vector f is going to be something about like that, somewhere up there. I don't know the coordinates yet. That's going to take a little doing, but this is like my best guess for where the vector f is going to be. Yeah, I predict that it will have an x-coordinate that's a little negative, and the y-coordinate will be bigger than either of the other two y-coordinates. All right. This is a rough picture, so don't feel that you can count the coordinates out here and get an answer, but it should give us a reasonably good idea of what this will look like. Okay. That picture is not strictly necessary, but it really helps me to get a sense of what we're doing. What we're going to do next is look at our two vectors, f1 and f2. This guy is our f1. This guy is our f2. And for f1, we're going to find the coordinates of that endpoint. Here is the formula for coordinates. I'll just remind you. A vector v, if we know the direction and angle, the x-coordinate is the magnitude times cosine of the angle, and the y-coordinate is the magnitude times sine of the angle. So, let's go ahead and do it. This is our vector f1. It's equal to the magnitude, which is 3, times cosine of 45 degrees. And the y-coordinate is 3 times sine of 45 degrees. Now, cosine and sine of 45 degrees, these are the ones where the cosine and the sine are equal to each other, and they're both equal to radical 2 over 2. So this is 3 times radical 2 over 2, comma 3 times radical 2 over 2. And we can simplify that just a little bit by just moving the 3 up to the top with the radical. Not too much else we can do there. 3 radical 2 over 2, comma 3 radical 2 over 2. So this is our formula for f1 for the components of f1. Now we're going to do the same thing for f2, and then we're going to add them together. So for f2, this one is, it's 5, that's the magnitude, times cosine 135, and then 5 times sine 135. And that 135, the reference angle here is 45 degrees, so it's going to look a lot, the cosine and sine are going to look a lot like this one, except that the cosine is going to be negative. So this one is going to have cosine of negative radical 2 over 2 and sine of radical 2 over 2. Let's go ahead and plug those in. This is 5 times cosine, we said, was negative radical 2 over 2, and then 5 times positive radical 2 over 2. Combining, we get negative 5 radical 2 over 2 and 5 radical 2 over 2. Now, these are the coordinates of this endpoint over here. These, 3 radical 2 over 2, comma 3 radical 2 over 2, are the coordinates of this endpoint here. What are we going to do with them? Well, let's go ahead and add them together. So this is to find the combination f, which is just f1 plus f2. Well, that is just equal to f1 is 3 radical 2 over 2, comma 3 radical 2 over 2, and that's going to be plus negative 5 radical 2 over 2, comma 5 radical 2 over 2. Adding two vectors together, we just add them what we call component-wise. So we add the x's together. That gets us 3 radical 2 over 2 minus 5 radical 2 over 2. And then we add the y's together. 3 radical 2 over 2 plus 5 radical 2 over 2. Now, some nice things to notice in the x coordinate here. We have a common denominator, 2, so we can just move it immediately into one fraction. And then what we're combining on the top, 3 radical 2 minus 5 radical 2, they're like radicals. They have the same radical 2, so we can do 3 minus 5, and we get a negative 2 radical 2 over 2 for our x. We have a similar thing on the right, common denominator of 2, same radical, radical 2, so we just add 3 and 5 and we get 8 radical 2 over 2. So this is our vector. We can simplify it a little bit more by canceling in the top and bottom 2 in each of these fractions. So the first fraction is going to be negative radical 2, and the second fraction is going to be 4 radical 2. It looks a little messy. I'm just going to clean it up slightly. Oops. Negative radical 2, 4 radical 2. Okay, and that's our solution to part A. Now, negative radical 2, that's the x-coordinate of it, is a little bit negative, and 4 radical 2, the y-coordinate, is positive, so this says to me it's going to be a little bit to the left of the origin and then up, and that corresponds to just what we got here. The coordinates of this guy, f, they are exactly this, negative radical 2 and 4 radical 2. Okay, that's our solution to part A. Let's go ahead and talk about part B. Oh, let's do one. No, okay, part B. In part B, let's go ahead and grab a copy of it. Here we go. Okay. So, in this one we see that the magnitude of F1 is 7, and the first angle, theta 1, is pi over 6, given to us in radians this time. If it helps, that's like a 30-degree angle. F2 has a magnitude of 4 newtons and an angle of 5 pi over 3. So let's go ahead and do some sketching, and then we will do our calculations. Okay. Pi over 6. So for F1, pi over 6, that's like a 30-degree angle. It goes up about like that. And the distance is 7. Goes maybe to about here. That's our F1. F2, the angle is 5 pi over 3. That's like going all the way up to here. That's pi over 2, 5 pi over 3. Well, where is this going to be located? 6 pi over 3 is all the way around. So 5 pi over 3 is going to be a little bit less than that. It's going to be down here. This is an angle of negative 60, or going around this way, 270 plus 30, an angle of 300. So, there, and let's see, right about there. This is our F2. Now, I can tell already that our final vector is going to be something like that. That's going to be our vector F. And we're going to go through the calculations to see exactly what that is. I'm going to expect that we have a slightly negative angle here, and that the length is longer than either of these two, longer than 7, longer than 4, but it's not twice as big or anything like that. It's only a bit longer. Okay, let's go ahead and work it out. We'll start with F1. f1, well, it's equal to 7 times cosine pi over 6, comma, 7 times sine pi over 6. And apologies, I'm going to go ahead and work in black from now on as it's easier to read. Let's see, cosine and sine of pi over 6. This is one that I happen to know. This is the one that where the two numbers go together. One is radical 3 over 2, and one is a half. And for this one, it looks like the x is bigger, and that means that the radical 3 over 2 is the cosine. So this is 7 times radical 3 over 2, 7 times a half, which is 7 radical 3 over 2, comma, 7 over 2. And that's how we're going to leave that one. Those are the coordinates for f1. Now let's take a look at f2. For f2, this is 4 times cosine pi over 6, times cosine 5 pi over 3, 4 times sine 5 pi over 3. Once again, 5 pi over 3. This is one where the cosine and sine go together. They're going to be radical 3 over 2 and a half. Here, the bigger one is the y, so it's going to be radical 3 over 2 is going to be the sine, and it's negative. The cosine is going to be a half, and that one is positive. So this guy is 4 times 1/2, 4 times negative radical 3 over 2. 4 times a half is, of course, just 2. And 4 times negative radical 3 over 2, we can cancel the 4 with the 2, and it gets us negative 2 radical 3. Okay. So here we have our first vector and our second vector in component form. Let's go ahead and calculate the sum. F is equal to, well, it's f1 plus f2. And that is equal to, it's 7 radical 3 over 2, comma 7 halves, that's my f1, plus 2 negative 2 radical 3, that's my f2. And then we just add them component-wise, so 7 radical 3 over 2 plus 2, that's our first coordinate, and then 7 halves minus 2 radical 3, that's our second coordinate. First of all, this is the resulting force, F. A little calculation, if we want to plug these into our calculator and get decimals, that helps for graphing purposes. The x-coordinate, 7 radical 3 over 2 plus 2, if we add those together, we get about approximately 8.06. And for the y, 7 halves minus 2 radical 3, we get 0.04. So what we have here is a positive x, and the y is positive but very close to 0. Now in my picture, you can see that that's a little bit off. I drew this in the wrong place. What accounts for this error? It's really a little bit up from here, and this is incorrect. Why is that? It's because I did not perfectly draw this and this. I didn't find out their coordinates in decimal and put them in first. But if I had done so carefully, we would have found that when I followed this to here, it ended up a little bit above, or same thing down here, a little bit above instead. So this is in the wrong place. Let's go ahead and fix it. We're going to put it in green instead. I'll delete this guy out here. And what is the change that I need to make? Probably, I'm going to guess that my change needs to be made to F2. So let's say that F2 really should go like that. And that is our vector F. Once again, this is a good indication that you can't rely on the pictures for the precise answers, but they do give you an idea of what's going on, at least what's a reasonable answer. Now, I just want to talk about one more thing, which is what is the magnitude Let's switch this guy back to F. What is the magnitude and the direction of this? So the magnitude of F, I think that's the part that means the most to me physically, is that's like how hard you're pushing on it. It's how much force in total is being exerted. And we can calculate that by doing the square root of 8.06 squared plus 0.04 squared. And altogether, that gets us into about 8.06 newtons. Now, something to notice was that our original forces, the size of F1, this was being pushed with a force of 7 newtons, and this was being pushed at a right angle to it at a force of 4 newtons. So I'm pushing away at this direction 7 newtons, you're pushing away at 4 newtons, but we're working at kind of cross purposes to each other, and the resulting force altogether, what are we pushing? We're pushing with a combined force of just a little over 8 newtons. So this, and the reason is that we're not pushing in the same direction. If we push in the same direction, the magnitude of the result would just be adding up the magnitudes of the two. But since these are going in slightly different directions, they don't add up straight. Yeah? They end up adding up to something a little over 8, and that's not the same as if you just were to add these two lengths. And that's just saying in a parallelogram, the distance across the middle is not necessarily equal to the distance along two of the sides here and here. In fact, if you think of this as a triangle inequality, so that this side should be less than those two added together. Okay. That's the force. And then, of course, we can do a similar thing from the angle if we say that the tangent of theta is equal to 0.04 over 8.06. If we get this in degrees, since that's where my intuition works better, this is 0.3 degree angle. You can see that this is a very small positive angle, and that corresponds with our picture here. All right, what was our final answer? Our final answer was this. This is our F, and that's how we can use vectors to talk about combining forces.